Morning, I'm Nancy Mullins. I'm a chemist here at Florida State College. I'm at South Campus. And many years ago, I had a student who was completely unsighted. And so normally you have students that have some visual issues. This is a student who had absolutely no vision and he wanted to take chemistry. And I said, okay, let's do this. I found somebody in town who knew how to braille and who knew how to braille in the science code, because there's actually a different language for science and math called Nemeth, and you have to know somebody who does that. I located the one brailler at the college that nobody'd used. It's like a printer that punches holes in the page or raised dots, and it hadn't been fixed. It hadn't been running in years, so I got that fixed. It sounds unbelievable if you've never heard a brailler. It's really something. And I had to think of a lot of creative ways so that he could have the same experience without having somebody tell him, well, Arnold, it's blue. Arnold needed to know that for himself. Actually, Arnold was sighted at birth, and he lost his vision due to a retinal disintegration when he was about 7. So he knew what blue was. But people who are not sighted still don't want to be told what it is. They want to experience what it is. And so I started trying to find ways so that Arnold could experience the class as well as anybody else. And what I discovered is that everybody wanted to play with Arnold's toys. that the class was very cohesive. The class was 100%, and nobody was uncomfortable working with Arnold. Everybody wanted to see, well, let's try it that way. And so I'd always like demonstrations. Don't go into the sciences unless you like demonstrations. But I always thought that it was more important that the students do the demonstrations for themselves where possible, so that they can discover it and have that experience. So one of the things that I ask students, they come into my office, is, what's your favorite toy? Because most toys that we work with are toys that are scientific based, can be used to demonstrate a scientific concept. We just have to look at them a little bit differently. Yeah.
Too much further along. My wife works with visually impaired people, so kind of curious, first of all, how long ago was this?
This was, 15, 20 years ago.
Yeah, that would explain a lot of the comments that are made by Nancy about this situation wouldn't necessarily be true these days. There are very few people who can use Braille as far as the level of sensitivity that's needed to actually be able to read Braille. A lot of people are not taught the math and science version of Braille, so that's further reduced in popularity. And there would be a lot of adaptive technology these days that would be utilized.
Absolutely.
Now, in case anybody does in fact have any visually impaired students, at some point in time, the college has a department, the VERC, the Vision Education and Rehabilitation Center. So that would be a possible resource for you. They do things like create Braille. They offer resources, they offer training, and so that might be something that you or your students might find useful in a similar situation to Nancy's.
Yeah, bearing in mind that our students are not all in this age group. That some of the students that are coming in are older and they actually did learn Braille. So that's sort of what's going on here. But anywho, you're absolutely right. The college does have better services now, but it didn't change the fact that the toys were the thing. And so that was really where we're headed with this. So Slinky, everybody has played with a Slinky. There are a lot of things that you can do with a Slinky that are even legal in most of the states. You can, of course, obviously wave behavior. You can show constructive and destructive behavior. What you know is that a wave brings energy, and that if we have two waves that occur at the same time, that they add to the energy, or they combine their amplitudes. If you actually had two Slinkies side by side, and you give them the same starting impulse, you're going to see twice the amplitude of that wave. So everybody's seen the demonstration where you're just creating a waveform. What I'm telling you is for exactly the same reasons. You have energy associated with a wave. And in the case of something that's physical, it has mass, it develops a certain amount of momentum. When you double the mass, you're going to get double the effect. And so it works actually great to show the Contu channel that's linked to the Blackboard site for this. On various sites where people have talked about the science of slinkies, because there are just tons of things you can do with them. So obviously there's the wave behavior. Everybody has sort of visualized it that way. Kindergartners are still learning cause and effect. Kindergartners are learning that when you push on something, that it's going to have an impact on it. And so from the time that we're talking about children that are pre-K up to college level, where you're talking about much more complex ideas, these things still apply. This is the state standard of physical science, standard 13. Transmission of energy. You have a system that's at rest, you give it kinetic energy, it then can transmit that energy through the body of the wave. Again, even a kindergarten standard. Conversion of potential to kinetic energy. Of course, that's when you put the slinky on the step and it's sitting at the top ready to fall, and then it does, converting to the motion. And then as you move along, it develops momentum, and that's what keeps it going. This was one of the most creative applications of a slinky I have ever seen. Does anybody know what a rheostat is? A rheostat is when you have changed the resistance of something. And so it's something that allows you to do that. So if you take your slinky and you're teaching physics or something along those lines, and you use binder clips and you attach it to certain segments of here. Because it's metal, it will conduct electricity, yes? So if I hook this into a circuit, so I've got a wire, I've got a battery, I've got a light bulb, I bring it back to here to complete my circuit. Depending on how far away the binder clips are, I have different resistance. Because the more of the metal it has to travel through, the more resistance you're going to see. Very cool idea. Even a very simple idea that you can teach a child. Not just physics, not just high school physics or college physics, but there's actually a very clear description of resistance being variable. Periodic motion, 9 through 12, you see this idea quite considerably. But I thought that was a brilliant application. Solar tube. Now, some of you have seen these, some of you have not. Solar tube is like a really long trash bag. A super long trash bag, 50 feet long. You get a couple people, you run it through a field so it fills with some air, and you close it off and you lay it on the ground. And as it's sitting on the ground and the sun's beating down on it, what's going to happen to the air inside the tube? It's going to heat up, it's going to expand, which does what to its density? It should make it less dense, right? And now it's going to float. Great demonstration of a number of concepts. Convection, that the reason we have winds, or space science, the reason you have wind currents is because one area is hotter than another.
These demos are on your YouTube.
Mm-hmm.
Are you gonna talk about that?
I have a YouTube. I have a YouTube channel that's associated with this. It's associated with people that did sign up with this, and I'll give you my YouTube playlist at the end and I just gave you samplings of some of these things. But convection currents, density and buoyancy. In 8th grade heat flow, they start seeing that at grade 4 because where's the energy coming from? Where's it going? How's it converting? it's going to heat, or of course the sun is providing both light and heat, but it's really usually the heat that's, although the light does part of it. Why? Because it's black. And so it absorbs the radiant energy from the sun in addition to just the heat. And it's converting it to what kind of energy? Kinetic, the energy of, or mechanical when you talk about large particles. So we're seeing a lot of different energy transformations with a very simple tool. Ideal gas law. Any gas law. I would sort of go with what Charles' law. Increase the temperature, the volume will go up. So basic gas behaviors. And it's just cool, let's face it. So many people haven't seen the solar balloon, but that's nice for a good afternoon. The love meter. Yeah, back in the old days, they used to call these hand boilers. They still do. If you buy it at Spencer's, however, yeah, you buy it at Spencer's, it's called a love meter. Yeah, it's a hand boiler. And of course, what happens when you grab the bottom of it? So what's happening?
Heating up.
Okay. So you'll notice that as, that's right, you are clearly warm. The heat is being conducted into the system. We have now heat transfer, heat flow. What happens that causes something to boil?
Heat it up.
Okay. You're making the particles move, and some of them break away from each other and go into the gas phase. And as the gas pressure builds up, all it has to do is overcome the atmospheric pressure. So once that happens, then it boils. So what is this stuff? It's actually probably dry cleaning fluid. I'm pretty sure it is. They put a little dye in it to make it interesting. So when you get them, they come in different colors.
No, it's not hot at all.
No.
It's just,
Oh, pass it around.
yeah,
Pass it
no, I was
around.
just joking. No, it's literally just like cold hot.
No, she's too hot for it.
Yeah,
Yeah, pass it around.
no, once you hold it for a minute, it's
Yeah.
just regular blood, no temperature at all.
That's right.
So I'm still hot.
That's how we know.
Flashes now.
All right. So as we're changing the vapor pressure, it overcomes the atmospheric pressure. Now what they do is they put a small amount of dry cleaning fluid in there. They remove some of the air, so they've reduced the pressure so it doesn't have to work quite so hard. But dry cleaning fluid, also has a very low boiling point. It's easy to convert, and therefore it's a good choice for that. So what are we seeing here? Obviously the definition of boiling point. Boiling point is when the vapor pressure at least exceeds the atmospheric pressure. Changes of state. Something is converting from a solid to a gas. You can't see the gas. We see the evidence of it based on the boiling. Equilibrium. Those of you who are teaching the higher levels, that as long as it's a contained system, you have every bit of that stuff there. It's just some of it's in the gas phase. As it cools down, more of it goes into the liquid phase. This is a really cool application. If you have never seen this demonstration, I have it on my YouTube channel. If you take that boiler, this is my boiler for a moment since it's moving around the room, and you put one side at room temperature, slightly warm, and the other side slightly cooler. Maybe you put it in a slightly cool water bath. Now it's going to take a while. You don't want a huge temperature variation, but you want a temperature variation, because what's going to happen is that as the warm side is heating up, it's converting to the gas. Now the cool side does what? It cools it back down into the liquid phase. But because it's a mixture, if you keep the temperature not a huge difference, maybe some ice in the water, but not too much, it'll leave the dye that they put in there behind as a residue. It is a very, very simple distillation apparatus. Now, one of my favorite things to do with the love meter is that you can actually make it boil by applying ice to the top of it. So what's happening? When you reduce the temperature, what happens to the vapor pressure?
When you reduce what?
When you reduce the temperature, what happens to the pressure of gas inside? It should go down. That's what Gay-Lussac's law of gases says. As the temperature goes down, then the pressure should also, which absolutely happens. So the pressure has now lowered. What little was in the gas phase doesn't have to work as hard, because if you can reduce the atmospheric pressure, then you can make it boil. This is why water boils at a lower temperature in Denver than it does in Jacksonville, because as you're moving up the directions. And so, very cool. Heat transfer, heat capacity, you can talk about that. You can talk about the fact that if that were water, in fact, you could build one of these if you wanted to. You just have to have some glass blowing skills. That's all.
And get the air pressure out too.
That's all, you big whiners.
Oh, really? What do they cost, $10?
Yeah, I've just bought a classroom set of them for my 2045 class, my Gen Chem class, as a demo, because they cost me like, I can assure you it wasn't that expensive because I'm cheap. And I bought this as my personal stock. So yeah, they weren't that bad. If you made one with water in it, it would not be nearly as good at it. Why?
Boils it.
Because of the boiling point.
Heat capacity. Water has a very high heat capacity, or specific heat. That's why it's a good coolant. So you provide heat to it and it doesn't change. It doesn't want to change temperature. Therefore, it doesn't want to build up vapor pressure because it's taken so much time to actually change its temperature. Now, you know that it's cold outside or it's hot outside, and you have the choice of sitting on the hood of your car or you sitting in the pool. Which do you choose? The pool, because of the heat capacity difference. Your car has a very low specific heat. It transfers heat very effectively, which is why we use iron for cookware, because we want the heat to transfer. We use water for cooling because we don't want the heat to transfer. We don't want the temperature to change very much. Higher level enthalpy of vaporization, that's the big fancy word for the amount of heat that it takes to make a liquid actually boil, to actually convert between the liquid and the gas phase. And so you can talk about the fact that that process is actually taking place and that it takes time. You are holding the love meter, but the whole time you're holding it, you still had some liquid in there. It takes some time because the more stuff you have, the more energy it's going to take to make it all fully convert. That's a really important concept for students, and that is the idea that heat is extensive. It matters how much stuff you have. My favorite example of this is if you have a pot of boiling water or a drop of boiling water. What temperature are they at? They're still boiling water, 100 degrees. However, one of them will burn you considerably, the other one will barely sting, because the pot of boiling water has more mass, therefore a lot more energy collectively. And so a lot of things that you can talk about when you're looking at this concept. Temperature versus heat. This is an idea that, honestly, when I see students in my college classes, they don't know this. I actually tell them the story of the thermometer, because their whole lives and your whole life, there's never been a time where you haven't had a thermometer available. But there was a time. And there was a time when the words heat and temperature were misused, used interchangeably, because we didn't know better. We know better now. So I would come into a classroom, I ask you, are you hot or cold in here?
Cold.
And I'm warm. Could have something to do with my thermal mass, but we're not going to talk about that. But what we're going to say is that that is a difference in perception. And so we need to find some way of making it so that we can compare it. So first person to actually do this took an evacuated tube, put some mercury in it, and measured how far the mercury traveled up the tube. And he found that at the boiling point, it traveled in the tube he was working with 212 millimeters. And at the freezing point, it traveled 32 millimeters. The word Fahrenheit in German means, Fahren means to travel. It says, how far did the mercury travel up the tube? That's all that really means. And so our 32 and our 212 were completely arbitrary because of the size of his tube and the mercury that he was working with. So somebody else came along and said, well, that's a ridiculous scale. Let's go with 100 between the starting point. And so that 1.8 factor is 180 degrees Fahrenheit compared to 100 degrees Celsius for the same amount of change. 1.8 times the Celsius. Add the 32 to correct for the fact you weren't starting in the same place. Nobody really ever thinks about that. And so this is one of those fabulous opportunities to talk about the difference. So temperature is, okay, first, what is a thermometer? How do we get there? Because you are actually seeing how a thermometer was developed. Temperature is how fast the particles are moving, which allows them to then break away from each other if they're moving adequately quickly. It's cold outside and you don't have gloves on. What do? You rub your hand. Do you do it slowly? No. So heat and temperature are related. Heat is the friction created by moving particles, and temperature is how fast they're moving. So the greater the difference in temperature, the greater the heat that's going to be developed from that. And so you can develop the heat equations for them when you're talking about this. Which brings us to the drinking bird. I love the drinking bird. From the time that I first saw one at my aunt's house, I said, I will always want one of these. I finally bought one. This is what happens when you actually get an expendable income. You buy stuff like this. Once the kids are out of the house, Mama gets a new drinking bird. That's it.
Oops. My keeps running out of water all the time. Evaporation is bad.
Yes. Now, drinking bird, honestly, it's a hand boiler. It's a hand boiler on a pivot. So if you never actually noticed that, he looks just the same. He's got a hat on, so you can't tell. So if you were to heat his bottom, you'd see the liquid moving up, and you can't actually see it. I've got freezing hands in here, but you can see it actually doing exactly the same thing. Now, what makes the drinking bird work is that as he dips into the liquid, his top is being cooled off. So he touches the water. So you get him moving just so he can touch the water. Then he has evaporative loss, and it cools him down. And now this is the ice on top of the love meter. He's cooled off. There's a pressure differential. The liquid's going to move more easily if he's cool on top. What's cool about this, okay, yes, it's the love meter on steroids, but it's also a really good description of intermolecular forces, because if you don't give him water to drink, but you give him your vodka, the amount you're willing to share with him, he's going to move at a different speed. He likes the vodka a lot. I'm not going to lie. He really likes the things that evaporate easily. And he's willing to work for vodka, apparently.
But I can't take vodka.
Yes, you can. You just call it something special. This is not vodka. You can get denatured.
For my bird.
That's right. But honestly, any substance that has a different boiling point would work. You want a big difference, rubbing alcohol will work. Boiling point, vapor pressure, all the same things, change of state. Intermolecular forces, because now you're showing why one thing evaporates more easily than another. So those of you who have to work with that. Change of potential versus kinetic energy. While he is in one position, he has, if he's in this position, he has what, high or low potential? With his butt up in the air.
High.
He has high potential because we have a weight that's elevated above the Earth, and we have gravitational potential. So he has high potential right now, and now he's converting it into kinetic energy. Just lots of little things that you can do with one simple toy. Center of gravity, potential energy, kinetic energy, which apparently I really liked. I put there twice. You do get the same periodic motion thing. And you can talk about frequency. How frequently does he drink? Heat capacity, energy transfer, all those same things that the love meter does for us. Radiometer. I love the radiometer. Radiometers, theoretically, are a scientific piece of equipment. That's the fancy word for things that we buy when we want to get it on a grant money. They actually make Christmas tree ornaments and things like that with the radiometer. There are a couple types of radiometers. This one is when they call it specifically a Crookes radiometer. How does that work? Have you ever seen one? All right, radiometer. You'll notice it has a needle up through the center. It is a slight vacuum. They pulled some of the air out of here. There's a glass cap that sits on top of the needle, and then one side of the vane is black and the other side is white. If you shine light on it, and sadly, the light that I brought didn't work. I don't know if this is going to work for us.
We got a cell phone with a light on it?
I don't think it's actually going to be strong enough. But if you shine light on it, sunlight will do it. Then, of course, the black side is going to absorb it. It's going to heat up. It's going to create convection current, and it's going to spin. Because there is some air in here. It's just not a lot because they want very little resistance to the spin. So the radiometer, very simple device. You can prove that it's based on the absorption of light if you were to take a heating pad. If the heating pad does one thing differently than light, you can look at the different energies of light. Does white light work better than blue light? Because it's all about whether or not it absorbs it. And so there's a lot of very simple ideas associated with this transformation of energy. Heat capacity, why does the black absorb more than the white side? Black body radiation, thermal energy and mechanical energy, convection, absorption and reflection. The white side is reflecting the light. The black side is absorbing. What is work? What is work? It's not what I get paid to do. Thank God. Work means you're moving something that has mass over a distance. So we've converted light energy into work because pretty much energy comes in two flavors. You're either doing work, you're moving something, or you're creating heat for the most part. That's where it goes. And so you actually have a little bit of both there. That concept is internal energy that says the energy of a system is either going to go into the heat or the work function associated with it. Now, my plasma globe sadly had a horrible death, and so I did not bring this in here. You can get them at like Party City. This is super awesome, aside from just being cool. Atomic emission. What we are seeing is they put a little of xenon in there, and that's the color that you see. It's typically xenon. They use some other gases. Got it. Yeah, he just gave me that. So you give it some energy, excites the electrons to move away. When the electrons come home, they release the energy. I'm going to give it energy. And now it's releasing the energy in the form of light. I'm going to put that right there. So atomic emission. Absolutely, you're seeing it there. Conductance, resistance. The substance doesn't conduct terribly well, but when you put your hand on the top of that globe, you conduct really well, and you'll see a good lightning bolt coming up towards your hand. If you put a plastic cap, like from a drink bottle, it won't do the same thing because the cap doesn't conduct. So you can show a difference in conductivity with that. Electrical current, flowing electricity. Again, if it didn't flow, then it wouldn't be conducting through me. Lightning. And hey, let's agree that it's cool. Voltage, electrical potential. This means that some things like to lose electrons more than others. Lots of things that you can do with this. I think we all, poor dog, he did not do it. Look at the look on his face. He had nothing to do with that small stain on the carpet. UV light shows fluorescence and phosphorescence. It shows how light interacts with matter. That the light coming onto this sample is one color. It's leaving it in another color, which means that it must have changed by the sample. Shows the difference between light just reflecting off of a surface and light being given off by the sample. You can talk a little bit about the energy of the electromagnetic spectrum. Molar absorptivity, big fancy word for some things absorb more than others. And it depends on what wavelength you're talking about. That sample or whatever that thing that dog did not do on the carpet, under white light wasn't obvious to us because it just doesn't absorb those wavelengths. But under UV light, it does. Did you know that chlorophyll is only produced with certain wavelengths of light? That's right, we need the UV because that's how chlorophyll is produced. If you don't give it the right amount of energy, it just doesn't do it. And so these are ideas, simple ideas with simple substances to work with. This is a personal favorite, magic sand. Have you ever worked with magic sand? You can see in the picture what it's like. It is builder's grade sand that they spray a whole lot of Scotchgard on. And when you pour it into water, it doesn't wet at all. If you actually dip your finger down into it, it feels completely bone dry, even while it's underwater. Zero wetting capability. We're talking about things that dissolves, like dissolves like. We're talking about the intermolecular forces. All those things are demonstrated with that. Because everybody has fireworks classes. Apparently, it is the thing if you go to raves. I am told that this is what happens. These are pretty inexpensive. You can get them for $1 or $2. I bought a classroom set years ago. The picture at the right was taken with my cell phone looking through the glasses at a discharge tube. And you can see the line spectrum associated with those particular atoms. So a very inexpensive way to give them the concept of atomic emission that show that white light is all the colors, but that with atoms, with those discharge tubes, it's quantized, it's only specific energies. Shows diffraction of light because there's actually a diffraction grating that's doing this, and you can talk about the prisms and the optics associated with that, and the wave nature of light, which is what diffraction really is. So lots of cool stuff there. Now, the point is that these are things that you see all the time. And I always ask my students, what's your favorite toy? Because there's usually some way I can work it into my lecture. There's usually some way that I can work it into something that they're going to do. And it's important that you do that. Because ultimately, we're all Arnold. We are all fascinated by the stuff that we can touch, that we can play with, that demonstrates some concept we're going to have to remember later on. And we're going to remember it better. So, for the awards portion of today, somebody have a sign-up sheet?